We're going to introduce self-organizing maps. So this is the algorithm that we are going to use through our experiments, and then therefore with this lecture we would like to go through it in kind of detail, and then we go to code, we implement this mechanism ourselves, and then we can apply it on our data. And before we start, we introduce this diagram again that kind of show where we are right now. So today's lecture is here. So we started to use the feature vectors we extracted, we calculated last time, and then to use it to train a self-organizing map. And then later we will use the trained SOM to do our experiments. And yeah, so I've taken 3 slides from the last lecture as a kind of reminder, because these 3 is kind of really important in the mechanism of self-organizing map. So we have feature vector. So we represent some objects with numerical features. For example, these 2, we use different values to represent apples and the persons respectively. And also we've introduced the Euclidean distance. So it's the distance between 2 points in the Euclidean space. And then these 2 points can be any dimension. So you can do it 2-dimensional or 3-dimensional or higher. And then we've introduced this combination of feature vectors and Euclidean distance. So these combinations allow us to calculate, let's say, to compare the similarity of objects. For example, then we can say how similar to apples is once we decided how we represent apples in a numerical way. So this is the 3 concepts we introduced last lecture. And today in self-organizing map, all of them are kind of included in its mechanism. And then so let's see what self-organizing map is. So SOM. So later I will call it SOM because it's kind of difficult to pronounce for me. So what is SOM? It's actually very simple. SOM is invented by Kohonen in 1982. It's actually a grid of feature vectors. If you want to draw a diagram, then it's like this. You have circles lying on the orthogonal grid, and then each circle actually represents 1 feature vector, and then this is it. So for example, here we are seeing is a 8x8x3 SOM. So we have 8x8 grid or nodes or SOM cells. And then each cell is a feature vector of 3 dimensionals. And then, so this is it. This is a self-organizing map. So it's actually quite simple. But then what exactly this thing do? So this is what we are going to look at in this lecture. For us, SOM can be understood as a projection from our data to a regular grid, or we can say that it's a kind of compressed representation of our data. What does this mean? So imagine that we have our data set, for example, in this case, a list of 3-dimensional feature vectors. We can have many of them, and then each SOM cell actually represents a cluster of similar items from our data set, which means some of the vectors, some of the items are projected to 1 cell, and some others are projected to another cell. And until all our data, all the items of our data somehow projected to 1 cell in the SOM. So this is the and then of course this representation is done by the training process, and then we will explain it later. And then so basically we can consider that this SOM is overall representation of our data set. And there's a very important concept called the best matching unit. So the best matching unit is the cell that, well, for the items of our objects, of our data set, their corresponding sum cell is called their best matching unit. So, so why, for example, why each item is projected on a particular cell, not some other ones? Because so this projection, this mapping is actually measured by the Euclidean distance between the element of our data set and the feature vectors of the sum, so the sum cells. So so the best matching unit is actually the cell that has the minimum Euclidean distance to the element to the item of our data set. So this is the mechanism. And so these are some very important let's say concepts. And then we would like to go more into detail to specifically how we train the sum from scratch. So what this training means is that at the beginning, the sum we don't. I mean, at the beginning when we have some data, we actually don't have the sum that, let's say, can perfectly represent our data. And then what we want to do is to approximate our data using the sum. And then which means we would like to adjust the adjust the values of the feature vector of the sum so that it represents our data set better. And then the process to making it representing better is called training. And we can start from this slide. So of course it's a dummy data set. So we assume that, for example, in this case, we have many apples. And then we have a lot of them, for example, could be 100,000 apples. And then we can't, let's say, manage them manually. But we know that some of them are similar to each other, which means we can, if we define the threshold of Euclidean distance, we can group some of those apples together so that it belongs to one group. For example, the red and the orange apple could be similar, and then the yellow and the green apples could be similar, for example. And then the training of the sum is actually the automated mechanism that doing this, let's say, cluster or grouping automatically. And how we are doing that is at the beginning, we create a sum with its feature vectors randomly initialized. So for example, if we have a in the Apple case, we have a 4-dimensional vectors, then we simply create a sum of arbitrary size with 4-dimensional feature vectors. So for example, here in this case, it's an 8 by 8 by 4 sum. And then of course we can play with the size, but then the dimensions we should always keep it the same as our data set. So the first step is simply randomly choose some numbers to create this grid, and then later the process is for each item of our data set, we pick it up and then we find its best matching units within the sum. So we calculate the Euclidean distance of this item between this item and all the sum cells. And then we find the one that has the minimum Euclidean distance. So this will be our best matching unit. And then after this, we select the best matching units and then its neighbor sum cells. So this neighbor means because sum is a grid, so that actually here we are talking about talking about two different two distances, and sometimes we may get confused. So one is the Euclidean distance that measures the similarity between vectors, and the other is actually the spatial distance between cells. So for example, in this case here, these surrounding cells actually have a distance of 1 towards the center, like let's say darker cell. So so in this step we select the best matching unit, which is in the center, and as well as its neighbors with, let's say, the radius or spatial distance of 1, so that we can have 9 cells selected. And then we update these cells based on the selected items of our data set, which is this vector. We update these cells. And then how strong we update all these 9 cells is based on how far they are to the best matching unit, which means this cell at the center is being updated, let's say, the strongest, and then the further other cells away from the center, then it's a little bit the update is more kind of lighter or small. And then after the update, we randomly move to another item of our data set, and then repeat this process, find another best matching unit, and then do another update process. And then we kind of do this process for all the items of our data set until all of them are visited. And then this whole iteration is called one epoch. And then we do many epochs during the training. We do many epochs with the shrinking radius, which means for the first epoch we may have a very large update radius, which means not only the best matching unit, but also their neighbors within a radius of maybe 5 or 6 will be updated. But then at the last epochs, only the best matching unit will be updated. So this is the whole mechanism of SOM. And later we will today we will try to implement the SOM ourselves through the code. So and then for the mechanism, basically this is it. And so for the topics like what exactly these SOM are good for, we decided to leave it to the next lecture. So basically, these are the topics that are correlated with how we are going to proceed our experiments with this particular algorithm. So today our goal is to implement it, to handle it ourselves, and to try to play with it, to try to visualize it, to get a feeling.
As Guo explained, this lecture will be all about the self-organizing maps and the way we can work with different type of data as well. So these examples are from some projects we did in the course of our PhD. And the idea is that you get a glimpse of how can you work with them. And the benefits or the different explorations you can do with SOM, these will be addressed in the next lecture. So, for example, we can work with 3-dimensional data. And again, these are considered as numbers, so we can extract their feature vectors and we can cluster them based on similarities and how they look like. And if we do a zoom on these clusters of objects, we see that there is kind of a consistency on clustering. Even though the computer doesn't know those were elements, they are encoded in a way that they can be clustered based on their similar features. So you see we have tables close to tables, doors close to doors, and so on. Another type of data that we can work with are images, and this is what we're going to do in this course. So these are more than 100,000 satellite images from around the world. And you see here, you again manage to cluster them based on similar features on their structure, for example. So last lecture, we explained you why it's important for you to decide how to encode each of your data, because that's how it's going to be clustered now with SOM. So I'm going to do a zoom again in this SOM, so you see it has an appealing of being clustered similarly. And we can also do it with the social media data or with images that contain people or landscape and so on. And in this, for example, the images were encoded based on the objects that were found in the images. So you see the cluster has a lot of meaning. So you have group of peoples clustered in one place, you have landscape in another, you have animals, you have food, and this is all because you choose to encode this type of data in a certain way. Because we've been stressing from the beginning of the lecture that any digital data or any type of digital data, it can be transformed into numerical vectors. And these numerical vectors are always talking about something of this image. So this is what we call the map of an image. So this talking in numerical terms of something is a map, and then the representation, or for example, this rendering of an image, then this is the model. So you can also work with text. It's another modality of data, and text can be also encoded in different ways. We already show you how to do it, and then here the text are somehow clustered in a way that similar meanings are close to each other. And another interesting feature with SOM is that you can also have more complex questions, such as how to identify change in satellite images. So therefore you need to compare two different stages and find the modification that happens through time. And again, here you can create a sum of, let's say, a mild, medium, or hard change in a way that you can navigate through this question you had at the beginning. And again, I have this other example with 3D graphic statics. And here, these are, again, we work with big data, so more than 1,000. I think here you have 65,000 graphic or 3D graphic for a roof. And again, we managed to cluster them because we treat them as numbers, and numbers can be clustered based on their similarities. So we wanted also to give you a small demonstration of how we can work with your collected tweets. And this has a lot to do with the lecture of the last week when we decide how to encode our data. So for example, here, what you're seeing is a data point or an image here. And we decided to encode this image based on their colors. So here in the center, you have the vector, the number vector. And then on your right, you see the sum. So here, what we are caring about, rather than objects, it's about the appealing or the colors of the images. So you can already identify this smooth pattern from the images. Here is a sum. So here it has nothing to do, it has people here, but also it has a building because the colors were similar. But this, for example, is answering one question. And also you can choose to encode based on the edges. So again, the vector, the numerical vector of this image is on the center, and then we see a different sum this time. All the time you're working with the same data, but you are encoding it differently. So therefore the render of the final sum is different. So for example, here we can do it with Fourier. As we said, Fourier encapsulates structure and color. So here you have, again, smooth changing pattern between some dark spaces to bright ones. And then now it's encapsulated both in color and structure. We have another way of encoding, which is this feature extractor, which is a convolutional neural net that is encoding the objects on an image. And here we will see that it's not anymore clustering based on color or appealing of the image, but more about the objects that are inside the image. So we'll see here we have a group of people, and that is getting, for example, here we have a city, we have animals here, and so on. So this is how you can actually start thinking how to frame your question. You need to know what are you looking for in your data, and then by choosing the right way of encoding your vectors, you can create a sum that is giving you a way to navigate through the plenty of data that you have crawled. So for example, here, this is a video, and I'm gonna show you the different ways. So you have to be aware that this grid that we are showing you are only showing the best matching units, or the images that are displayed here are the ones that have the closest distance to the best matching unit. And inside these cells, you will find another group of images that are close to the best matching unit. And what you're seeing in this video are all the images that are contained within this cell. So that's how you check if your self-organizing map is working properly. If all the images that are included in the group are similar, then you can be sure that it's working proper. Yes, so now what we're gonna do, we're gonna work with SUM, and Guo will give you on call, he will give you the explanation on how the self-organizing map is built up, and then we will work with the data we have crawled. So this was a very quick and fast explanation on how we're gonna work, and now I'm gonna stop sharing my screen and Guo will continue.
Yes.
One last thing, if you haven't done that, please download the code and slides from our website. Then you will be able to follow us. Now with Mathematica file, you will find it there.
Okay, yes. Now oops, sorry. Yeah, now I can start sharing again. And yes, so if you download today's Mathematica, I think today there's only one. It's called 08 Psalm, and then it's a date. So yes, can you see my screen?
Yes.
Okay, good. So so this is today. This is the file that we are going to work with today. It has 3 chapters. The first one introduce how SOM works. So basically, we are going to go through what has been introduced in the slides using code. And then the second is to create your own self-organized map on the Twitter you've been collected for the last 2 weeks. And then the third chapter is working with SOM. We decided to leave this part for the next lecture. This part allows you to do more operations. For example, doing query, doing predictions, doing some visualizations using SOM. And then today we are going to go through the first and the second chapter. And also here on top, we have 2 links. So just in case you haven't got enough data from the crawler, you can play with this sample data we provide. There are 2. One, the first one is the one I'm going to play. It's some old tweets that we collected when we were tuning our Twitter crawler. It has around, I think, few thousand images, and it has a size of less than 500 megabytes. So you can, if you want, you can download it just as an example. The other is a very small demonstration project we made before. It collects the tweets from main cities of Switzerland, and it has 8,000 images collected from 26 cities. It's like 1 gigabyte size. So yeah, if you like, you can start to download these 2 dummy datasets, and then we can play with them later.
I think
and now
they can also work with the data they have crawled.
Yes. Yes. So just in case if they don't have enough data on their hand, they can play with these 2. Yeah. So now let's start. So let's so first how sum works. I will make it bigger, 125. Yes. And as I introduced in the slides before, that actually sum is a grid of feature vectors, and we can implement that with Mathematica using simply one line of code. So sum equals to random real between 0 and 1, and then we have size is 8, and then dimension is 2, right? We run this cell, we say yes. And then, yeah, here it is. This is our sum. So actually, so you see there are 8 by 8 squares, no, rectangles. And then we see in each rectangle, there are 2 numbers. So these 2 numbers is the feature vector. And then, yeah, so here is one feature vector, and then here is another, and then another, and another. They are in an orthogonal grid. So, and then the best matching unit. So imagine we have another vector is 1, the first dimension is 1 and the second is 0.3. So this is our, let's say, query vector. And then we would like to calculate the Euclidean distance of this vector between this vector to all the sum cells. And then we would like to get the one that has the smallest or lowest Euclidean distance. So if we run these lines, this cell, then you see here we have a result of a grid and also an image. So this grid shows the Euclidean distance between our query vector to all the cells of the sum. So you see that here is 0.7, 0.8, 0.9, and then it gets larger, some get smaller. And then if we map these numbers into black and white, we get another image showing here below, right? And then from this image, we see that actually there are some pixels that are really dark, which means the Euclidean distance is really, really small, and then some are really bright, which means their distance are quite large. And then the BMU, the best matching unit, is to locate the cell that has the minimum Euclidean distance. So in this case, I assume it will be the one in the center because it looks really dark. And then the second code, the second cell, what it does, it extracts the one that has the Euclidean distance that are nearest to 0. So this is the function we're using, nearest. And then here is the mapping between the values, the Euclidean distance, and the location they are in the sum. And then we get the one that are closest to 0, and then take it out from the list. Yeah. So actually, each operation is just one line of code, and then the other code are just for visualizing. And then if we run this, we see that yeah, I should move this small window. Yeah. Then we see that actually here the BMU is located at the row 4 and the column 8. It's not the one in the center, it's the one on the right. So it's this guy, 0.9 something, and then 0.3 something. And then if we go back to our query, then we realize, okay, it's really quite similar because the first element of our query vector is 1. And then of course we can play with it. Let's say we change it to 0.5 and 0.6, and then we get something else, right? And then if we check the BMU again, then we find, then it is located to another cell. Now the BMU is located at the row 5 and the column 2. When you are running this code, the result you get probably is different from it's different with mine, because actually we initialize these numbers randomly, and then because each of us has different random seed at the beginning, therefore we may have different results. If you want your result to be, let's say, as exact as I'm showing here, then you can use random seed. For example, you can say random seed, let's say 1. And then in this case, I think if you insert this line of code at the before you creating the sum, and then first every time you run this cell, the result, oh, it's not the same. Shit, it should be the same. Okay, something is wrong here, but never mind. Let me just check seed random integer. Ah, it's called seed random. It's not random seed. Sorry. Okay. Yeah. So after you set the seed, for example, to 1, then first every time you run this this code, the result will be the same. And if you take it out, then every time you run it, it will be a different grid. So with random seed, it's helpful to let's say have a synchronized result between us. So here I'm using 1. So just in case you want to have exact the same result as I am, you can also use 1. And then I run this part again. And then in this case, the BMU is at row fourth row and the first column, right? And then so these so these are the Euclidean distance and the best matching units on sum. And then the important part is training, because eventually we want to use our sum to represent our data, not just some random numbers. Therefore, we need to tune the values of the sum so that it represents our data better. And then, with the case of this query vector, so I'm gonna still use 0.5, 0.6. So to do a one-step training as a demonstration, and then as I explained in the slides, that the training not just change the value of one cell but many cells. The reason of this is that so that we can get a kind of consistency between the adjacent sum cells, so that the distance between best matching unit, assume that we have two elements, the distance between their best matching unit can reflect their actual distance, which means if they share the same best matching units, then they to be very similar. If the distance of their best matching units is quite far away, then probably they are quite not similar. So this is the idea why we need to change multiple cells at the same time, not just one. And assume that we are going to working with the changing radius of 3. And then therefore the first step is, so I mean, all these operations are done on top of the result that we already have this best matching unit, which is at the fourth row and the first column. So based on this information, we are going to update this cell and the adjacent cells with the radius of 3. And then if we run this code, basically the critical part is only this line. So this update equals to let's say the inverse of the distance of each cell between the best matching units. Therefore, for the best matching unit itself, the magnitude of the update will be 1, which means the largest. And then for all the cells that are lies within the radius of 3, they got some other update magnitude, which becomes less if they becomes further towards our best matching units. And then for all the other cells that are out of this range, the magnitude for update will be 0, which means they will not be changed during this step of training. And then we can also visualize it as an image. So you see that it's centered at our BMU, and it kind of fade. It kind of change from bright to dark when the distance gets larger, right? And then after we have this magnitude for update, we can update the sum cell, use this simple rule. So basically, we know our target, which is the query vector. We know the values, the old value, which is the sum old, and then we know their differences, and then we multiply these differences with our update magnitude, and then we put the result, we add the result to their old value, so we get the new value. So you see that here, if the update is 1, then we change the old value completely to the new value, to the target. If the update is 0, then we didn't touch anything, because then the sum new will be equals to sum old. And if the update is, if this value lies between 0 and 1, then we get something that lies between the target and the old value. So this is the training part. And then we implement this with this one line, and then we visualize it with another line. So this is the result we get after training. So you see that here, this best matching unit, the result would be 0.5, 0.6, which is exactly the same as our query vector. And then for the other vectors, if we compare it a little bit, then we see that they are changed, but not completely. They are kind of lying between our new values and their old values. So this is the mechanism for training. And then this is the manual training for just one item of our data set, and then we can write the above code into a small function so that we can train it automatically. So for example, here I wrote this small function so it does everything at the same time. So you see that here actually the code is exactly the same as those I showed before. So first I calculate the Euclidean distance, then I find the best matching unit, then I calculate the magnitude of updates for all the cells, and then I calculate the new sum based on the update and the value of the old sum. Yeah, and then I do this. I do all this code. I loop all this code for each element within our data, and these elements called query, and then this is our data. And then the input is a sum, a data, and then a radius for update. Right? So I run this, and then here again I initialize the sum from scratch. I say seed random. Let's 3. Let's change it. So so that I can start. I can have a fresh start. So this time I have 2-dimensional vectors, and I want to interpret it as colors. So the first dimension represents the phases of colors, which means blue, red, or green, and the second is the saturation. Yeah, saturation. Yeah, and then if I initialize this sum randomly, then and to color this the grid based on the rules that have been set, then this will be the result I have. And if you set this seed random 3, then I think you will get the same result as mine. Yeah, and then now we have the sum. We need to have some data. So this line, with this line of code, I create my dummy data set. So it has 6 centers, and then there are some scattered points lies around each center, and then so that I got a kind of random data set, not completely random, but still have some pattern. And then I can also visualize this data set in the similar way, so that the color actually represent the location of not the location, the value of their feature vectors, right? So you see there are 2 axes. One is the phases of the color, and then the second is saturation. And then one thing before the training, one thing I would like to mention is that, so actually how we are visualizing our data point here is in a 2-dimensional Cartesian grid, and then we can do the same thing for the sum, so that we can know that the position of each sum cell, where the position are for each sum cell in this space. So for example, if we overlap our random sum and our data set, this is something we get. So here we have 8 by 8 is 64 nodes. These small dots represents our randomly initialized sum, and then these lines represents the adjacency between the dots. So you see, actually here is a kind of chaos because all the dots are initialized randomly, and then they lies here and there, and then because they connected to each other somehow, and then these lines are basically crossing the whole figure. And then what we are trying to do is to tuning the values of these dots so that they on the one hand covers the our data set, and then on the other hand they are not, let's say, chaos anymore. The adjacent dots are becomes similar to each other. So now comes to training. Because we already wrote this function that does the training for us automatically. Therefore, what we need to do is to specify the radius that we are going to use during the training. And practically, for a practical reason, usually the radius we are going to use will decrease. So for example, we can start with a relatively large radius like 6, and then eventually reduce it to 1. The reason for this is that at the beginning, at the first few epochs, we would like to somehow sort it out for the entire sum so that it's not any more chaos. And then for the latter epochs, we do a kind of fine tuning, which means we tune the values of each node, let's say, more precisely. Therefore, usually we have a decreasing radius, but then of course you can also play with some other patterns of radius, and then you can see how different this radius affect, how the different radius affect the results. So here I'm going to stay where I am here. So I will choose from 6 to 1 as my radius, and then here I had a new trick. I have a small trick that I name the sum as new sum, and then I use this new sum to do the training, and then therefore I can somehow get the history of the training, and then this sum remains the same, remains as it has been initialized. And if I run this, it may take some seconds. So actually here, the training is only this line, and then the rest lines are kind of doing data collection for the later visualization process. Okay, it's done. And then if we visualize the trained sum in a similar way as we did here, yeah, this is the results. So you see that actually the numbers and the colors of the sum grid are changed, and also the precision of the sum grid, sum cells lies in this two-dimensional grid, two-dimensional space also changed as well. So you see that now it's not anymore, let's say, chaos, but more organized. So you see that actually adjacent cells are lying in a very closed location, and then they kind of represent similar things. And if we visualize the whole process, because we have 1, 2, 3, 4, 5, 6 radius, therefore we have 6 steps of training. If we visualize all these steps, then we can see how from the beginning, this chaos status, the sum begins to tune itself, and then try to distort itself and try to cover our data set, right? Yeah. And of course you can play with the size and also the dimensions here, but then here I will not change the dimensions, because then I can't visualize it using colors as I'm doing here. I can change the size. For example, I can change it to 4, then I get a new random sum, and then I run the rest code again. then you see how the size can be played. And then radius, I think here I can cut the first 3 radius and only leave 3 to 1. All right, I train it, I visualize it, then this is the new song, and yeah, and also to check the training history. Yeah. So yeah, so this is kind of a quick explanation of and as well as implementation of the self-organizing map. And then now we are going to use a very simple example to show how SOM can be interesting in applicational level. So let's say that we have an image. Actually, I took this code from Ludger. Let's say we have this image, and then we want to know let's say, what are the major colors being used in this image. And then therefore, at the beginning, I can randomly choose 1000 pixels from this image, and then I take their color data out. Therefore, I got the list of vectors. It has a dimension of 1000 by 3, so I have 1000 vectors with 3 dimensionals. And then I can use these vectors to train the song. And then here I don't use my code anymore. I use a more let's say efficient implementation. I do it like say 16 by 16 the size, and then here is the training. Yeah. And then because we have 3 dimensions, we can have 3. If we slice them for each dimension, then we can have the visualization for each dimension. And then you see at the beginning they are randomly initialized, so they are kind of chaos. And then after the training, which is 4 epochs, we got this smooth pattern here. And then the output, I think it represents well the color scheme of our input image, right? And then after we have this song, then we can start to play with it. For example, if we have another image, we can do the same to get all the color data of this image, and then we can find the best matching unit of our new color, which is coming from this image, the second image. We can find the best matching unit for our new color, and to get the nearest answer from our song. Here, the answer means that I calculate the best matching units of our new image towards the song, and then I return the value, the feature vector of the BMU back. So it's a kind of doing a prediction, which means I feed the song to some with some vector, and then I get some other vectors back. And then the answer I have here is always the feature vector that are trained from the first image, which is this one. So I think it's done already. And then the last step, I can reorganize the colors, the answer colors into space, so that I can show them as an image. And then you see that actually is the same content, but rendered in different color. Yeah, this can be a very could be an interesting example how SOM can be useful.
Reminder for all of you on how to work with it. So then we go to where we have crawl our tweets. So I have lectures, 8 code and data.
You have to unzip it.
Yeah, just a second. Polybox, lectures.
You need to unzip. Yeah.
No. All right. Then I choose this one. It's done. I'm loading now. I'm specifying the vectors. So polybox Map&Models, lecture 8, code and data, all tweets, and then I'm gonna work again with the vector of a feature structure. I open it, and then I will keep on running the lines. So I see it's working, it's loading all the vectors and extracting from this meta file only the numerical vectors here in this line. And I'm again gonna train the sum on 8 by 8. Okay, it's taking longer.
Oof.
Oh.
Because the dimensionality is quite high because it's 2048, therefore it's kind of slow. We did our experiment with our large computer in the chair, so maybe we didn't realize it's a little bit slow on the.
I think what we could do is to use the vectors of semantic analysis. Yeah, 3 is a list of 3 values, so I'm gonna do it with that. I mean, it's good that we are doing this now with you, so you know how much time it takes you to actually train your sum, so you know how long you need for that to work on. So you see, it's very fast now. So if I check my backlist, first 3 elements are three lists of 3 elements containing the semantic analysis on text. So I'm going to train my sum of 8 by 8. I can also do it a rectangular. So I'm just gonna do it like this. So you see, you can play either to only have it only in a square format or rectangular. And here I'm gonna train. You see, it's very fast because vectors are only 3 dimension. And here, here you see I have created already and exported my sum. So as Google said here, what you have to take care of is to always define where are your crawling data and with which vector you're going to work with. And then here, the third part is if you have already trained a sum, you can import it, meaning that when you have done this training, you can close your Mathematica file, and then you can start working with this, so you don't have to train it again. So training, you can close it. You only need to define your directory, where are you with your directory, and then just load in your vector, your sum, I'm sorry. So here I'm gonna load one sum that was already trained. Waiting. I'm loading it. Here. So it's giving me here what you see is the number of the best matching unit. So we have a grid of I don't want to of 10 by 10, and then it's telling you how many elements are included in that cell. So we can visualize the sum in different ways, and one way will be to, as we did it here, so to tell how many elements are in each cell. But also, this is very interesting that you can define a pattern to visualize your sum, meaning you can decide whether you want to have it in a smooth changing pattern of green to pink or on aquamarine colors. And here, for example, we choose the dark rainbow, but we can choose any one. So here we gave you the list and also the example of how it will look like. I'm gonna run this line for you, and you see. Now my sum, as it's trained, it gets this smooth changing pattern from blue to red, which was defined by this color scheme, and you can choose anyone. So this is already a very personal approach on how to render your sum. So first, you can render by knowing how many elements are inside each cell or in. And then you can decide how you're gonna colorate it based on the cluster. So you see there is a huge cluster in red in my sum and a small blue. You can also do it with keywords. So here, what this code is doing is extracting maximum three keywords from all the text, and it's gonna visualize it on top. And you see there is a different size, and the size depends on how often this word was used in the text. So it's so what you are seeing now, even though this sum that I load was trained with vectors of images, you can still visualize it on text. Just to emphasize on something here at the beginning, when I was training and importing my sum, I trained it in a small. I trained it smaller, so I did 8 by 10. But now I import one that I have loaded. Okay, so another way of visualizing your sum is with this word cloud function from Mathematica. Is doing similar to what you're seeing here with the keywords, but actually, if you check what word cloud function is, I'm going to show you quickly. It's with a list of text, with a text, it already gives you a kind of an overview of what is happening there. So you see in this, it's asking for the text regarding country data and population. And now it's giving you which are the countries that have more population. And then you can do it in different ways. So this is the function that we're using here. And it's how in this way we're making the words bigger depending on how often they were used. I think this will take some time. I wouldn't run it now because I think we're getting shorted on time, but you should run it on your computer. Another way of rendering your sum is by defining or choosing a random image from your database. Also, one thing that is very important is that what we introduced you at the beginning about this best matching unit. So the images that we're seeing here are the closest one to this best matching unit. So sorry, what you can do by choosing the closest to the best matching unit, but what you're doing here, we are choosing from the pictures that are included in the cell randomly. It's very fast in this way, but if we want to have it only visualizing the closest one to the best matching unit is this one that is called nearest image. It's taking longer because now it's finding the closest Euclidean distance from the best matching unit to your data points, but you see here, we see a kind of a consistency in clustering. So we have this landscape on one side, we have city here on the top, then we have some faces here, and we have group of people. One thing that is very important for us, that I mean for you, because you have to, this is for the task for next week, is that you will have to create these put in 3 renders together. So you will have to make a screenshot of this line where we see that you have created your sum based on images, on text, and then how many elements are inside your sum. In this way, we keep track first on how many images you have crawled. If you have crawled correctly, because you will have to have text and then you will have to have images. And here in these 2, we will see if the text you have written in this Google Doc regarding how you vectorize your data, it makes sense. So if you said, I'm gonna I'm gonna vectorize my data based on feature extractors, we will see here a self-organizing map based on objects, or if you encoded your data based on the appealing of the image or the color of the images, here will be a different render. So this is very important for us. This is what you have to deliver for next lecture: a screenshot of these 3 sums in a row, so we can keep track of these 3 things that I have already told you. And one last thing with this code that you can do is here, this is interesting as well, So you can specify one number cell. So here you see the numbers in this sum here. You see the numbers, the cell number 1 contains 56 elements. So you say, I'm interested in this cell. So I say, I want to look at cell number 1. You run the cell, you see, you're sure that you're getting this one. And then I'm gonna see all the elements that are inside this cell. And in this list of information, of data, you can click on any of these, and then you will be redirected to the Twitter page, and then you will see where this image was coming from. You can do it with a different image because you said, okay, yes, I think based on these clusters, the one that I really want to look at is this one. So it's cell number 50. Cell number 50 has 66 elements. And then you see here, you see where it's located. You say, yes, it's correct. And then you run this last line where you see all these images here.
And also, just one comment. Also, when you're visualizing the elements, you can play with the numbers so that you can visualize more or visualize less, lower.
I'm going to just change the cell. So
yeah,
we see different examples. So here, for example, you're gonna, instead of 5, I want to see 10, because here you see I checked cell number 31. I see there is 34 elements, so I can even increase to 20, but just a matter of visualization, I do it with 10, and then you see here all the elements. I can increase the number here by 20. Another thing that is interesting is that here with the highlighted cell sum, you can visualize it on the text, but you can also do it on the images, right? I think here is image. Right, Goa? Like that.
I think so, yes, but I don't remember exactly.
I'm just gonna check that quickly.
No, go below, because I think we have highlighted some using images, just not this one. No, go below. Working with some, I think. Highlight some by location, time, keywords. Yeah.
Method image, yes. So if you want to visualize your, instead of, because by default here, it will always show you with text, but if you want to see it with the image, then you have to say, I'm going to use the method of image. And then you run the cell and you'll see that instead of showing you the text, is showing you the image that you're selecting. So here depends, either you're more, you want to focus on text or an image, then you will have this. So I'm going to repeat the task for next week. You have to make a screenshot of this row. And then you will have to show us that you have explored a little bit of your sum. So you select one cell, again, a screenshot of this, and then a screenshot of the cells, the images that are within that cell. So that will be the tasks for next week.